Now let us consider one example. So your 5 cards are drawn at random and without replacement from a deck of 52 cards. So 52 choose 5 is the total number of possible cases in which 5 cards can be drawn from a deck of 52 cards without replacement. Because when it is without replacement, the cards are not repeated. So that is as good as saying that you have drawn all the 5 cards together. Let us look at B is the event that all drawn cards are spade. A is the event that among drawn cards at least 4 are spade. C is among drawn cards there is a king of spade. So let us say all these 3 are there. Now there is some amount of dependence because B says all drawn cards are spade. A is among drawn cards at least 4 are spade. So there is some dependence over here because they talk about the same spade cards over here. So let us look at what is the probability of B given A. Probability of B given A is same as probability of A intersection B by probability of A. But let us look at what is A intersection B. A intersection B is among drawn cards at least 4 are spade. B says all are spade. So if B holds, then anyway A holds because all are spades implies that at least 4 are spades. So B implies A. And in mathematics you know that if an element of B implies element of A, that means B is contained in A. Now if B is contained in A, then this A intersection B is same as B. So this probability of A intersection B becomes probability of B divided by probability of A. So let us look at what is the probability of A. Probability of A is total number of possible cases is 52 choose 5. Cases favorable to A among drawn cards at least 4 are spade. Sorry, let us look at what is, at least 4 are spade. So that is the probability of A. At least 4 are spade means exactly 4 are spade or 5 are spade. So let us look at what is the total number of cases in which you can get 4 are spade. 4 are spade, that means there are 13 spades cards, you get 13 choose 4. 4 out of those cards you get, and 1 card you get from the remaining 39 cards. Then all 5 are spades, that can happen in 13 choose 5 ways. So that turns out to be probability of A. Now similarly probability of B turns out to be total number of cases is 52 choose 5. B is all drawn cards are spade. So that means all the 5 cards are spade. So 5 cards can be chosen from 13 cards. 13 spades card is 13 choose 5. So this is what it turns out to be. So probability of B given A turns out to be this divided by this. And that is what the next formula says. Now similarly probability of C given A is same as probability of A intersection C by probability of A. What is the probability of A? Let us look at. Probability of A is among drawn cards at least 4 are spade. What is a C? Among drawn cards there is a king of spade. So what is the probability of A intersection C? At least 4 spade and C. What is the C event? Let us go back. C event is there is a king of spade. At least 4 spade and 1 king of spade. At least 4 means 4 spade, 5 spade, 1 spade king, 1 spade king. So 4 spade and 1 spade king means the 3 spades and 1 spade king. So these 3 can be chosen from 12 because 1 spade king is must. So that can be done in 12 choose 3. 1 spade king would be 1 choose 1, that I am not writing down over here. Then what is remained is only 1 card that I can choose from remaining non-spade cards in 39 choose 1 ways. Now let's look at this situation. This situation is 5 spade, all are spade, and I want 1 king of spade. 1 king of spade can be chosen in 1 choose 1 way, and I want 4 remaining spade cards. So remaining spade cards leaving king is 12, and 4 can be chosen in 12 choose 4 ways. This is total number of ways. So this is the required probability. So our next result is about one of the very important theorems in probability theory, and it's called the theorem of total probability. I think this is one result which is the most widely used result in the probability theory. Very basic result, but very widely used. So let EI be a collection of mutually exclusive and exhaustive events. They are mutually exclusive, that means they cannot occur together. That means EI intersection EJ is fine. They are exhaustive, that means they constitute all the possibilities in the sense of probability. Or in other words, probability of union I belonging to S, EI is 1. Then for any event E, probability of E is same as summation I belonging to S, P of E given EI, E intersection EI, which can be written in terms of conditional probability as summation I belonging to S, P of E given EI times P of EI. Now an application of this result could be in the following sense. Suppose E1, E2 and EK, they are K causes for any event to happen. So any event can happen due to occurrence of the events E1, E2, EK. Or in other words, any event E can occur with the occurrence of one of these events E1, E2, EK, which are mutually exclusive and exhaustive. Then probability of E is same as probability of E intersection EI and sum over EIs. And this is not as a very surprising, because if you consider P of E to be some kind of a measure, then what it says is measure of E is same as the measure of E which is contained in E1, a part of E1, the measure of E which is contained in E2, so measure of E which is a part of E2, and then finally the measure of E which is a part of EK, and you sum it over it. And since EI is the total measure, this looks like a reasonable formula. Now let us try to prove it. The proof is very simple. I'll use the fact that if probability of F is 1, then this implies that probability of any event A is same as probability of A intersection F. The result proof is very simple. I have given this as one of the home assignment problems earlier, but by theorem of, you know that probability of A can always be written as probability of A intersection F. So try to do this, and probability of A intersection F complement, right? This is due to this fact that A is over here, F is over here. So I am trying to look at what is probability of A. So A intersection F is this, A intersection F complement is this, and since P probability function is additive, so probability function of union of these two, which is probability of A, same as probability of this, which is A intersection F complement plus probability of this. Once that happens, then probability of A I write down like this, and then I see what is the F complement. Probability of F complement would be 1 minus probability of F. So probability of F complement is 0. If probability of F complement is 0, probability of any subset which is contained in F complement, that would also be 0. So A intersection F complement is contained in F complement, whose probability is 0. So this would imply that probability of A intersection F complement is also 0. So this becomes 0. So that is why probability of A is same as probability of A intersection F. So this I also gave as one of the assignment problems. If probability of F is 1, then probability of A is same as probability of A intersection F. And that is what exactly I am doing over here. Probability of union I belonging to S EI is 1. So probability of any event E is same as probability of E intersection union I belonging to S EI. Now this E gets distributed over this union. So this is same as union I belonging to S E intersection EI. But EIs were mutually exclusive, that means they were disjoint. And E intersection EIs are contained in EIs. So EIs are disjoint, E intersection EIs are contained in them, so they would also be disjoint. So if they are disjoint, then P being a probability measure, so probability of union would be same as sum of the probabilities. That is what is happening over here. So I have proved this part, which is same as probability of E given EI into probability of EI. So that proves the theorem of total probability. Now let's come to another important result, which is called the Bayes theorem. As I said, this theorem would be applicable in situations, suppose, where any event E can occur due to occurrence of event E1, E2, EK. So this E1, E2, EK could be a cause of events. And you are interested in the occurrence of any event E. So what Bayes theorem says is, given that the event E has occurred, what is the probability that it has occurred due to cause EJ? and that is what it says. So this is what this is there. The proof is straightforward. Proof follows from theorem of total probability. So it says that EI belonging to S be a collection of mutually exclusive and exhaustive events. So same assumption as the one in the theorem of total probability. Then for any event E, probability of Ej given E turns out to be this quantity. Let us try to see what is the probability of Ej given E. This is same as probability of E intersection Ej by probability of E. But probability of E by theorem of total probability is whatever is there in the denominator, and probability of E intersection Ej can be written as E given Ej into Ej, and that proves the Bayes theorem. Let us try to see this remark. So as I said before, for example, these Ej belonging to S could be possible causes of occurrence of any event E, and these causes are distinct and exhaustive. So that means any event is occurring, it is occurring due to the effect of these events Ej's only. Then probability of Ej given E can be interpreted as, given that the event E has occurred, the probability that it was caused by cause Ej. So if such a probability has to be found, use the Bayes theorem. Now in Bayes theorem, these probability of EIs are called the prior probabilities. So these are the probabilities which were given to you in advance. Probability of EI given E are called posterior probabilities, because these probabilities, so these are modified probabilities after you have information that event E has occurred. So probability of EI was probability that cause EI is the cause for the occurrence of events, that is given by P of EIs. This is a modified probability, and that is why it is called the posterior probability. Let us consider this example. So suppose there are two balls, ball B1 and ball B2. B1 has 3 red and 7 black balls. Ball B2 has 8 red and 2 black balls. All balls are identical except color. A die is cast and ball is selected as per the following scheme. So I select ball B1 if 5 or 6 balls show up, otherwise ball B2 is selected. So to select one of the balls B1 and B2, I play a game, and that game is casting a die. And if the outcome of the casting of a die is a number 5 or 6, I select ball B1, otherwise I select ball B2. Now after ball has been selected, I now select one of the ball at random from the selected ball. The first part is find the probability that the ball is red. Second is, given that the ball is red, find the conditional probability that it came from ball B1. So let us look at B1 has 3 red, 7 black. Let us look at B2, the ball B2. Ball B2 has 8 red and 2 black. Now ball B1 is chosen if and only if the outcome of casting a die is number 5 or 6. B2 is selected otherwise, that means any other number comes up. So I define the events EI as that ball BI is selected, R as the event that red ball is drawn finally. But you see, to get R is the event that red ball is drawn. So let us look at what is a P of R. Now how ball is selected? It is selected based on the outcome of casting a die. So probability of R is same as probability of E1 intersection R plus probability of E2 intersection R, which can be written as probability of R given E1, probability of R given E2 into probability of E2. So this is red ball, not red bowl. So I define EI to be the event that ball BI is selected. So what is the probability of E1? Now I know that ball B1 is selected if 5 or 6 is a result of casting a die. So getting a 5 or 6 in casting a die, number of favorable cases is 2 by 6, which is 1 by 3. So of course probability of E2 would be probability that bowl B2 is selected. B2 is selected if any other event is occurring, any other number is occurring, which are 4 in number. So this is 2 by 3. So what you see is E1 intersection E2 is 5, because you know that either E1 bowl B1 is selected or bowl B2 is selected, because that is what our scheme tells. Either you can get 5 or 6, or you can get any other number. So B1 and B2 cannot occur simultaneously. So E1 intersection E2 is equal to 5. Probability of E1 union E2 is 1. So they are mutually exclusive and exhaustive. So I can apply the theorem of total probability. Probability of R is same as probability of E1 intersection R plus probability of E2 intersection R, which is same as probability of R given E1, probability of E1 plus probability of R given E2 into probability of E2. Note that to get a probability of R, that red ball is drawn, I need to have an information that I am drawing a ball from which bowl, whether I am drawing from bowl B1 or bowl B2. So that means I should have an information whether event E1 is occurring or the event E2 is occurring. That means whether bowl B1 is selected or bowl B2 is selected. And that is why I have used this conditional probability. Now once I am dealing with probability of R given E1, it says my bowl B1 was selected. Bowl B1 was selected, it has 3 red and 7 black balls. So probability of getting a red ball is 3 by 10. Then what is the probability of E1? We have already seen 2 by 6. So that comes over here. Then probability of R given E2. R given E2 is the probability that you draw a red ball from the bowl B2. Bowl B2 has 8 red and 2 black. So probability of drawing a red ball from bowl B2 is 8 by 10. Then what is the probability of E2? We have found it out, 4 by 6. If you simplify it, it turns out to be 19 by 30. Now let's look at the second part, where you are given that red ball is drawn. What is the probability that it came from bowl B1? So that means probability of E1 given R, which is same as by Bayes' theorem, probability of R given E1 into probability of E1, which is same as basically this whole quantity is same as probability of E1 intersection R, divided by probability of R. Probability of R, in fact, I have found out over here, which is 19 by 30. What is the probability of R given E1? That also we have found out over here. That is the first term over here. Probability of R given E1 into probability of E1. So 3 by 10 into 2 by 6. So if we simplify all this, this turns out to be 3 upon 19. So we saw a nice application of theorem of total probability and Bayes' theorem through an example. Now let me give a few problems. Now we have seen that the conditional probability is a probability function. Using that, try to prove these two results. Let A, B and D be events such that probability of A is positive. Try to show that probability of B given A satisfies this relation. Similarly, try to show probability of B complement intersection D complement given A is same as this quantity. So take these as assignment problems. Their proofs are almost straightforward once you use the fact that conditional probability, which is P dot A, is a probability function. Now let me introduce the next module. Let me give the summary of the next module. Now in next module, we'll discuss the concept of independent events. Now here what we have done is we have defined the concept of a conditional probability. So probability of an event A given that the B has occurred. Now if this turns out to be probability of A, so it says given the information that B has occurred, the probability of A remains unaltered. So the conditional probability is same as the unconditional probability. If that is the case, it suggests that possibly A and B are independent. That means occurrence of B really does not affect the occurrence of A. So this shows us the way to define the concept of independence, and that is what we'll do in the next module. So let me conclude this module over here. Thanks for your patience and have a great day.